So my name is Radek Simko. You can find me on the internet as Radek Simko pretty much everywhere. I work for HashiCorp, as I've been introduced. I work as part of the Terraform team, maintaining the provider land mainly, mostly AWS, but I contribute to other providers as well. And I built the Kubernetes provider, which was announced recently. So a quick show of hands. How many of you are operators mainly? Who deals with infrastructure? Okay. And who is a developer mainly? Just a few hands. Okay. So it's mainly infrastructure guys here and girls. So who uses AWS? And and GCP, Google Cloud? Okay, a few hands. Good to know. So let's talk about why. Before we dive into how, let's talk about why. Why would you want to go multi-cloud and manage multiple clouds together? So modern infrastructure is fairly complex, and it consists of many different things that can fail. So any component of the server, like disk, or memory, or motherboard, may fail, or maybe the whole physical machine can fail. Maybe the whole rack can fail, or you can experience a network or power loss. Or maybe the whole data center may fail, which typically involves a natural disaster due to a failure of multiple power sources or network sources. Or even a group of data centers in multiple geographic locations may fail at the same time. Accidents like this may be rare, but they do happen. And to be fair, it's hard to prevent them even at the scale of Amazon or Google. That wasn't me. So both of which have, big pool of engineers and money obviously behind them. And these outages cause problems as you suddenly cannot serve your customers. So one of the reasons you would probably want to go multi-cloud is availability. Now let's talk about two cloud providers, AWS and GCP, in a bit more detail. AWS has 16 regions. I hope you can see that. The gray is not very well rendered. Around the world, and 44 availability zones, including one on the US West region for just purely for US government, and some services that that Amazon offers are only available in certain regions. In case of Google Cloud, Google has 12 regions, as the last time I checked, and 36 zones. And again, some services are only available in certain regions. So let's talk about the workload. You may have an app which has variable workload like this, where it just varies. You have that much memory, that much CPU over time. Or maybe you have more CPU heavy workload. Or maybe your app behaves like this, where we are consuming a lot more memory than a CPU. And Amazon offers you pre-shaped instance sizes, which you may or may not utilize completely. So depending on what's your workload, you may be wasting some resources, either memory or CPU. Whereas Google gives you this, provides you much more flexibility. They allow you to choose as much or little CPU and memory as you want. So you don't have to stick with pre-shaped instance sizes. And it turns out that computers can break sometimes. There may be a faulty piece of equipment which needs changing in the data center, or the underlying operating system or BIOS need upgrading, in which case the data center or the operator is called to perform the maintenance and replace the faulty piece of kit. And this is the way Amazon deals with the maintenance problem. They send you an email notifying you, hey, we have really important news for you. Your instance may be unreachable already. And they basically tell you to relaunch the instance elsewhere on unaffected hardware. So it's your responsibility to basically do that. There are ways to kind of do that semi-automatically, but generally speaking, you still have to build that automation. In case of Google Cloud, this fairly complicated diagram describes live migration in GCP, which what it means in practice is that the maintenance event doesn't require customers' attention and usually doesn't cause any downtime. So Google did a demo at Google Next where they were streaming a HD video from one of the VMs, and they were as they were migrating it over to a different VM elsewhere on a different hardware, and you didn't see a glitch. So it seems to be working very well. Now, it depends, obviously, what's your workload and how do you treat your instances. So let's talk about pets. Who's got pets at home? Anyone's got a pet? Yeah? So if you've got a pet, you know that you take very good care of them. You know, you take them out for a walk, you make sure they are healthy, and so on. And anyone's got a farm here? No? Not many farmers in the audience? So if you've got a farm, you know, you've got a cattle, you use the cow to get the milk, make cheese, and I apologize to any vegetarians, and then you kill them eventually. So there is a lot less emotional connection with the cattle as opposed to pets. And if you look at the relationship between those two and you apply that to servers, then you may treat your servers as pets or as a cattle. So depending on how you treat your servers, that's how you may choose, and you may or may not like these two different approaches that Google or Amazon offers. So the next reason why you would go multi-cloud is cloud-specific features. Now, pricing of any cloud provider is very complex. It involves many different variables, so you can't easily tell that one is cheaper than the other. Because it depends, again, on your workload and the way you use the cloud provider. This is just a simple comparison that I pulled off a blog post somewhere between AWS, Azure, and GCE. But as you can see, it just really depends. And this is most bigger providers let you buy their unused capacity for a workload which isn't time sensitive. They call it, Amazon calls it spot instances. Google calls it preemptible instances. And that's where it gets most interesting, because each provider may offer you different price based on the current capacity and the utilization of their data centers. So this is a graph for the EC2 spot instances. And you can see that it may vary in time. So another reason is costs. That's why you may want to look into multi-cloud. And one final reason that is perhaps competitive reasons. So you may have reasons why you want to avoid a particular provider because you may be someone like Target, who is in the retail industry, and you just happened to hear the news that Amazon bought the retail, what's their name? Yeah, basically it's getting too big for you, and it's a competitive threat. So HashiCorp makes tools which reflect the multi-cloud API agnostic reality. Vagrant is one of our tools which allows you to manage dev environments. Then we make Packer, which allows you to bake your machine images. Console, which is our solution for service discovery and health checking. Then we have Terraform, which is the one I'm going to talk about, and the one you're going to see in the demo. That's our solution for infrastructure management. Vault is our secret management. And Nomad is our globally scalable workload scheduler, which I'm going to talk briefly about as well. These are all open source. You can use them for free, and we also offer a few commercial offerings, which is how we make money. So infrastructure is an overloaded term. So let's take a look at what you can manage with Terraform. So here we have, this is really just a snippet. The number of providers is really like high. But we have some sort of traditional cloud providers like AWS or Google or Azure, or maybe bare metal like Puppet. And then you can see Heroku in the middle, which is basically platform as a service. And VMware at the bottom as well. Then you can manage things like Bitbucket or GitHub, so version control systems, not necessarily the content in the repositories, but things like users, teams, and permissions around these. Or Datadog and Librato, which are the monitoring services. And you can also manage databases and users for those databases of different kinds, like MySQL, Postgres, Console, etc. There may be some overlap with Vault, because Vault is generally the slightly better solution for managing secrets and sensitive data, but that would be for a different talk. So let's talk about Terraform. One of the things you will notice is that it uses its own custom language, which we call HashiCorp config language, HCL for short. And even if we set the manual management of your infrastructure aside, because that usually doesn't scale, even if you're not using Terraform, you would be building your own scripts or your own solutions directly in a high-level language like Python or Go. And you would need to deal with all these idiosyncrasies and nitty-gritty details of APIs. You would need to understand how they work, what fields you need to pass in at any given time, etc. And eventually, because hard coding all your details of your infrastructure in the code base is probably not a great idea, you would realize that you need some help from other languages which are designed to handle data, like JSON or YAML. And those languages on the left side offer you plenty of ways to shoot yourselves in the foot. They give you very sort of complex things like classes, functions, for loops, etc., which makes the whole code a lot more complex. Whereas on the other side, you have the languages which were designed to handle data. So they lack these features. They don't have typically classes and functions and for loops. But they also lack features which you may find useful for describing infrastructure, which is like referencing or comments. You can't do either of these in JSON. You kind of can do that in YAML, but has anyone ever tried doing referencing in YAML? Yeah? I think if you tried, you know what I'm talking about. So that's why, despite that designing a DSL is a challenge, both Puppet and Terraform have chosen this path. So HCL is a separate project which you can find on GitHub, and it is used in various GitHub HashiCorp projects like Console, Vault, and Nomad, and Terraform. And the nice thing about HCL is that it's JSON compatible, which is useful for generated code. Now you may ask, why would you want to generate the code? So here is an example. GDS, which is the Government Digital Service in the UK, takes advantage of this in their solution for DNS management. They basically take zone files for bind, they convert them over to JSON, and then hand them over to Terraform, which will then create DNS records in GCP, Dyn DNS, and Route 53. Now, let's talk about efficiency and what kind of efficiency you can get from Terraform. So we have an instance here, Google Compute instance in this case, and that's how you can describe an instance in Terraform. And let's take a look at the at the config. So we give it a name. We say basically how much CPU and memory do we want, because Google also has some pre-shaped instance sizes. You don't have to use them, but you can. And then there is a zone. Here we basically say we want to boot off the Debian image, and then we say we want Google Cloud to assign the IP to the instance automatically. Now, the nice thing about Terraform and the language that it uses is that you can use these references here. What it means, basically, is that we create the DNS managed zone here, and then we create the record, which references that zone here, and then we can also reference the public IP of the instance, so that the record points to the instance effectively. Now, once you have that config in place, you can run Terraform plan, which is a command that gives you this nice output, which basically tells you what's going to happen before it's going to happen. So before you make any changes, how is it going to affect your infrastructure? And here we see that we don't have any existing infrastructure created yet. So we are adding 3 new resources. And as you can see, here we are applying, which is actually making the API calls to GCP. And you can see that it's creating the resources in the right ordering. So Terraform will first pick up the DNS zone. Hopefully you can see that. Then at the same time, it also starts creating the instance, and eventually the instance is booted. It's finished the whole process of creation, and then once we have the instance, we can create the DNS record which points to it. And the reason Terraform is able to do that is because it uses the graph theory to basically map all of the resources, all of the configs that you've seen on the previous slide to a graph, which looks like this. So here you can see how it maps the relationships between the resources, and the other reason why the graph is important, other than relationships, is because it can decide which resources can be either deleted or created in parallel. So here we can see that the instance and the zone can be created in parallel. So that's what Terraform does. So first we go from the bottom to the top. We first create the instance and the zone, and then the record, because that obviously requires both the instance and the zone. And you can actually get to see this graph yourselves if you have your own set of configs and generate it directly from Terraform using Terraform graph. If you want to hear more about the graph theory and how it applies to infrastructure as code, you should definitely go and see this talk from a colleague of mine, Paul Hinsey. The slides will be available later on, so you can follow the link. And now coming up, full life cycle. Why is it useful to cover the whole life cycle? Some people think that creating resources is like that's the step to production. You know, we just create stuff and then we can go live. So this is how you can create resources in Google Cloud. And in reality, it actually turns out that we need to update them after a while. And we need to, in order to update them, we need to know how the APIs work exactly, because some fields may conflict with each other, and some things are just not updatable at all. And you need to figure out the right ordering of the operations. Like, you know, first we need to create the new if we are replacing an instance, we need to create a new one, then add the record for the new instance, then delete the old one, and delete the instance. And eventually we need to delete the resources when we are decommissioning the app. Now, this is just a snippet of code from Terraform's code base. That's not necessarily something that user would need to deal with, but Terraform has this thing called schema. And that's where we, developers of Terraform, translate the API's behaviors and quirks to make the user's life easier. So we translate that to the schema. Basically what you can see here is that this field called identifier, which is exposed to the user, has a type, it says it's optional, and it cannot be updated, which is what the force new says. And it conflicts with another field. And we perform some validation as well, which is quite useful to see that you've done something wrong before you actually send it to the API. Now, most cloud APIs you'll ever deal with are asynchronous, which is usually good for scalability. But users usually ask for feedback, and you don't get certain important attributes that you may need, like IP address, out of the API until the resource has actually finished provisioning. So that's why, again, this is another snippet of the Terraform's code base. It's not something that user has to deal with because it's hidden in the code base in the functionality of Terraform. So here we just basically list all of the pending states of a database, and we wait until it's actually available, and we have some timeouts in place, etc. So here is a plan that you can see in case you're changing a field that is mutable. As I said, some fields are mutable, some are not. So metadata for a Google Compute instance is a mutable field, so you can change that, which is what the plan reflects here. That's why it's yellow, and that's why it just says 1 to change. Whereas if you decide to change something like a name of the instance, that's not, because it's used as a unique ID for the instance, it's immutable, so you can't change that, and that's what the plan reflects here. It's red, it says forces new resource, and the plan basically tells you, hey, there may be an outage, because we are going to bring that instance down and then spin the new one up. So keep that in mind. Now let's talk about Nomad. Nomad is the workload scheduler, as I mentioned, and it allows you to, it uses HCL, and it's globally aware, which means you can run that in multiple regions and multiple data centers. And it allows you to run both containerized and non-containerized workload, as opposed to some other schedulers. So you can run both Docker and Rocket, some Java applications based on JVM, or whole VMs via QEMU. And it's also cross-platform, because it's written in Go. We take advantage of Go at HashiCorp, and Nomad is available for Mac, Linux, and Windows. And you get a single binary for both the server and the client. So here is an example of a task, web service in this case, which uses the Docker driver. And here we just pull down the Redis image of the Docker Hub. Here is another example of a binary that we run, and we pass in some arguments. So that's just the exec driver. So you can run binaries as well. And if you're a developer, you may run Nomad locally and try out most of the features without having to build your own cluster, which is quite useful. So it's time for demo. Let me run this first. Let me switch displays. All right. Right. So, who likes watching the this terminal? I enjoy it. Yeah. But not enough hands, so I think we're gonna dive into the configs, because this is gonna take a while. This is gonna take a few minutes. So let's take a look at what I built here. Well, let me rephrase. What I intended to build. This was my intention a couple of weeks ago when I was preparing for this talk. In fact, I managed to build all of that. We have the Amazon Web Services here, and that's the region that I built that in London region. So basically a cluster of 3 Nomad nodes and a Bastion host. I did it properly. You know, it's not all on public internet. So we have a VPN connection in between the GCP and Amazon. And I did the same in GCP. And then we exposed those services running in Nomad through the load balancer here. And the bit I didn't actually finish is the DNS here, which is like the global, what I thought would be like a global load balancer, DNS-based load balancing, because I had some troubles with the load balancer in Amazon, because it doesn't give you an IP address by default. So that's quite, we don't have that bit there. So let's dive into the configs. So we have to, so let me pull that out. We have 2 directories here, one for AWS and one for GCP. They are very similar. They have some definitions for DNS, load balancers, network, security, and the VPN bit. So let's dive into AWS first. And let's start with the network. I hope you can all see that. So we have the VPC here, which has some tags, and we take advantage of a data source called availability zone, which comes from where? From AWS TF, here we go. So here is a data source, and the difference between resources and data sources is that resource creates stuff, updates stuff, and it has basically a CRUD interface, so create, read, update, and delete. That's what it's capable of. Whereas data source only has the read of the CRUD. So it can pull down all the availability zones available to you in the region that you're using. So that you can do things like this, like create a subnet, one subnet per AZ. And then here we have a function which calculates the subnet CIDR for us. So we don't have to do that manually. And then we say that we want one subnet per availability zone, and it belongs to the VPC. And we have some private subnets, one per AZ, and public subnets, one per AZ. Then we have elastic IP address for our NAT, because obviously we need to get out to the internet. We have internet gateway and a root table. And then we have our Bastion host that you've seen on the slides. And we just give it a, a small instance. And here we have another data source, which is quite useful, because if you ever dealt with AMIs in Amazon, or even in images in Google Cloud, it's quite difficult to stay on top and always get the latest image. So that's why we have this data source here. I just need to find where it comes from. I think it comes from here. So here I used a stable channel of CoreOS, because I like CoreOS as it's very lightweight. And here we are filtering the AMI based on some filters in the architecture. And we make sure that it comes from CoreOS. So that gives us the AMI ID, which we use for launching the instance. And then we have some security groups, and we give it some permissions through IAM. Here is a special block called lifecycle, and that allows you to change the lifecycle of the instance. So how it behaves when you run apply, and the replacement of the whole resource is required, because by default, if you were to if you were to replace the instance, or if Terraform was able to replace the instance, it would first delete the old one, then update any references and destroy, and then create a new one. So this basically reverses that order. So it first creates a new one, updates the references, and then deletes the old one. So that's very useful if you have resources with unique names, for example. And then we have an ASG, auto-scaling group. Is everyone familiar with auto-scaling in Amazon? Yeah? Cool. Mostly. Yeah. So for those of you who are not, just a very brief overview, it allows you to spin up a number of instances and keep them. If one dies, then the ASG will basically spin a replacement instance for you. So let's see, how are we doing? Right, so we created 104 resources so far. It's great. That's in both GCP and AWS using a single command, Terraform apply. Yeah, so that's how you do multi-cloud. And let's just take a look at the load balancer. That's probably the interesting bit. We have application load balancer here in AWS, and we can use variables as well, which is the bit I probably didn't explain. And you can define variables like this, which allow you to make very reusable configs that you can share amongst your teams. And you can give them some default values as well. So that's what it says. It's basically going to interpolate the value of the variable. And here we have just a listener, which basically says, from port 80, which is where the user comes in, use the HTTP protocol and direct it to Fabio. The bit I didn't mention is that I'm going to use Fabio. I'm going to schedule Fabio using Nomad, because Fabio is a nice way to do the load balancing and service discovery. Well, basically uses console to figure out which services and where are active, so that it can direct the traffic appropriately. And this is pretty much the same, just for different services. So let's see if I can find the IP of my Bastion host, because I run my Bastion host as in auto-scaled group as well, because sometimes, why not? Sometimes people do crazy things. So let's try and connect to now. This is obviously, you all do that, right? Don't look at me, don't give me that look. Actually, when I was at the conference earlier today, it seems someone was doing man in the middle on the public Wi-Fi. I was just getting different certificates, so this is probably a bad idea. But anyway. Now we find the IP for the Bastion host in AWS. There's the only public IP that's exposed. Here we go. Now we are in, and we can SSH further from there. So let's see, this is Amazon. So Amazon, let's take a guess. Maybe won't take a guess. I'm going to connect to one of those. That's 13. And let's see if console was able to form the cluster. Yay, we have console running, and it formed the cluster within AWS. And the reason it was able to do that is because I leveraged this new feature of console, where you can basically use the Amazon's API or the cloud provider API to discover the nodes that you spin up as part of an auto-scaling group using tags. So I just defined the tags in here, and I said this is running in AWS, and that's how they found each other. And I did pretty much the same thing in Google Cloud. For which I need to find the IP again. That's 5, for example. Eventually. Oh, is it 1010? Here we go. So console members, we can see that it also has its own cluster. Yeah. So we have 2 clusters, one in each provider. And we have very similar config in here. It's just got GCE and the same tag. So now let's see if Nomad was able to talk to console and form a cluster as well. Yay, that's working. So we have Nomad working, and one useful thing to note is that both console and Nomad have this nice UI. So you can, this is actually new. You can see this, clients and servers and jobs that you have scheduled on the cluster, which are none at the moment. So you're going to see that in a minute. But let's join the clusters together. So server join, I believe that's the one. Just need an IP of one of those. Joined one service successfully. Node status. Let's see. Yeah, 2 have joined already. The third one, come on. Here we go. Nomad node status and GCP sees it the same way. So you have 6 node cluster, which is across both AWS and GCP. And now we can start scheduling stuff. So let's take a look at GCP, because I wanted to show you the GCP part as well. So we have what's the meet-to-bit network. So similarly to AWS, we have a Google Compute Network here, which doesn't define the CIDR as opposed to Amazon's VPC. But it allows you to define the CIDRs as part of the subnetwork. And subnetworks, as opposed to Amazon, are region-wide. They are not zone-wide. So that's quite useful for global, like more flexible load balancing. And then one thing that Google does not have, unfortunately, and I'm hoping that it will soon have, I'm looking back there, the back seat, the Google guy, is NAT as a service. So I had to build my own NAT instance here. So that's what this all is about, basically. And the NAT instance has got its own cloud config, which is somewhere here. So that's what I had to do, because there is no NAT as a service. And then we have the static IPs for the NAT, because if you're going out to the internet, it's useful to use the same IP so that other people can whitelist it in firewalls, etc. Now, is there any other meet-a-bit that I should show you? Maybe load balancers? Security. Security is the interesting bit. So firewalls work differently in Amazon and GCP as well. If we look at AWS security, you can see that you basically assign security groups to something like instance or a load balancer. And then you use that basically to identify the source of the traffic or the destination. And then you have those ingress and egress rules where you reference those security group IDs or IPs in this case. But here we have we have an IP here? Here we go. So here is a security group for the load balancer, and here I'm basically saying that my front-end instances, those are the workers that are part of private private subnet, that I'm able to reach them from the load balancer. So that's what this says. Whereas in GCP, things work a bit differently. I would say, just my personal opinion, it's a bit more flexible and maybe easier to work with once you get used to it, so that you can assign tags to instances, and then you have those firewall rules which are applied to tags. So it's kind of, the relationship is different, and you can allow, here I'm allowing port 22 from a CIDR, from this source range, and I can say it comes from the, that's firewall rule for the Bastion, and I can say that it applies to Bastion, which has this tag. So you don't have to reference this, it's just for simplicity reasons, because I like to reference things so I know where they come from. So they can, both firewall rules and the instances can be created independently. So that's a nice thing that you get in Google Cloud. And then we have some firewall for the VPN. So let's take a look at this here. So this is the top level Terraform config, which uses modules. And modules are basically provide you a way to make reusable configs again. So here I'm encapsulating all of the AWS logic in a module. And here we say it comes from this directory, and what region to use, etc. And then we have the GCP module. And the benefits that you get in Terraform is that you can, excuse me, you can create the AWS and expose, basically create all of the parts of the VPN connection first, and then reference things like the VPN pre-shared key in GCP on the other side, so they can talk to each other and they connect. They create the VPN tunnel effectively. So let's see. Shall we do it in GCP or in? I'm gonna schedule Fabio first, which is a nice project created by Frank Schrader, who now works for HashiCorp. He used to work for eBay, and that's when he created Fabio. And it's as I said, it's kind of a load balancer which talks to console, and that's the service which allows it to see which services and instances are active. So let's see, what do we have? Fabio. So this is a job file for Fabio. I'll first schedule it and then I'll show you what's inside. Nomad run Fabio. So that's been scheduled. As you can see, it's been scheduled 6 times because we have 6 node cluster. So it's been scheduled in both AWS and GCP, even though I ran this from GCP. And yeah, we should see that here as well, actually. It's starting, and as it's starting, we're gonna take a look at the config. So here we define where it's gonna run, in which data centers. We define the type of the job. The type could be a service or a system job, which basically means run this job on every single node once, which is exactly the right use case for Fabio because it's a load balancer. And then we have a group, which is very similar. For those of you who are familiar with Kubernetes, group would be something like a pod in Kubernetes. And then we have the definition of task. In this case, we are downloading Fabio binary of GitHub, and we just check the checksum so we know it's the right binary. And we specify some resource limitations here for the CPU and memory. So let's see, how are we doing? We can use Nomad status, Fabio, to see if it's running, and it is indeed running. So as Fabio is running, we can also check. It doesn't have any routing yet, but it exposes this nice UI. And we can also see that it's registered in console, hopefully. Fabio here. So you can see in console that it's passing the health check, so the Fabio itself. So now it's time to schedule something a bit more useful. It's a fairly simple job that I've written earlier, which I called Nomad Echo. And all it does, let me schedule that first again. All that does is it prints you the ID of the node and the IP address, so we know that the load balancing is actually working. But other than that, it's very similar to the previous job that you've seen, except that we have type service here. So we get to define the count, the number of instances of this group. So it's going to run 6 times, and regardless of which data center does it use. And it's gonna download this binary of Amazon's S3, check the checksum, and then it's gonna expose this service using Fabio. That's why we are basically using these tags here, because Fabio uses tags in console to basically do the discovery. And then we specify resources as well. So let's see, how are we doing? Status Nomad Echo. Okay, some are running, some are pending. Oops. Let's close that. Let's wait for the 2. Come on. Yes. So now if I go to the bit that I didn't show you actually, that I should show you, is that I have a URL map that I used in, that I use in the GCP part. And the URL map, which is here somewhere, here we go, that basically says if the host name contains, and this is for, here we go, Fabio hosts, yes. So if the host name begins with Fabio and has a dot and then the DNS name, then basically direct the traffic to Fabio, and the same goes for Nomad and console here. And then we have a default rule somewhere. Yeah, eventually. Anyway, let me show you Nomad Echo. So we have hello from Nomad, and we can see that this is served from GCE because this DNS record points to the global load balancer in GCP. And if I refresh, you can see that it just picks a different instance every single time, or almost every single time. So 2, 4, 6, etc. And now if I go to AWS, it serves the same thing just from AWS data center in London as well, 10, 5, 27. So that was my demo, and I have one more slide and then I'm done. So to recap, think about multi-cloud, but before you do that, think about the reasons why you want to go multi-cloud. one of them being availability, the features that each cloud provider has to offer, and how that's relevant to you. Think about the costs, because nobody likes to waste money. And use cloud agnostic tooling, because that's future-proof. That will allow you to migrate off one provider to another. So thank you for your patience.